In this video, which is the last video for chapter 7, we're going to look at why orbitals have the shapes that they do. And so just as a refresher, if you're at n equals 1, your orbital looks like a sphere. N equals 2, the p orbital, your figure 8. N equals 3, your d orbital looks like two figure 8s crisscrossing. N equals 4, your f orbitals, you have 8 balloons. They're really funky, so we don't need to talk about that. So remember Schrodinger's equation. When you square his wave function, you get a probability density. You get the probability of finding an electron versus distance. Okay? And the way we talk about this is called a radial distribution function. A radial distribution function basically says, at a certain distance from the nucleus, what's your probability of finding an electron? And it's radial because you have to think of all 360 degrees. You have to think about this in a giant circle because we're in 3D space when we do this. We're not in 2D space. Anywhere where you have a probability of 0, we call that a node. Okay? So let's take a look at the s orbital. That is where n equals 1, therefore L equals 0. And it's the lowest energy state that you can be in, n equals 1, L equals 0. Your electrons are the most stable in this energy level. If we look at the RDF, it's very high near the nucleus, and then it just drops off. And if you were to plot this probability versus distance, and that's what these dots are, you will get a sphere. And that is why the 1s orbital is a sphere, because the probability high near the nucleus, and then it drops off as you get away from the nucleus. Okay? Now if we look at the 2s, or n equals 2, L equals 0, 3s, n equals 3, L equals 0, and we look at the radial distribution, we get you're still very probable near the nucleus, but then you have a region of space where probability is 0, and this is called a node. Then you have high probability away from the 0, or away from the nucleus. Now, if you were to look at this probability density, you would assume, probability density is huge near the nucleus, so you'll always find it near the nucleus. But if you look at the total radial probability, it is a very small probability to be by the nucleus and higher to be further out. Because when you're thinking about radial space, you're in three-dimensional space, so bigger circles, like the one I'm showing here, has more area than smaller circles. And since these bigger circles have more area, you're more probable to find your electron there. So 3s we have 2 nodes now, and you can see in the probability distribution our third sphere is the biggest by far, and since it has more area, you're more likely to find your electron there compared to this inner sphere or this inner sphere. Okay, so that's the 2s and 3s orbitals radial distribution functions. Now let's look at the p orbitals. That's when L equals 1. And when L equals 1, we have 3 m's of L levels, if you remember. -1, 0, and +1. And all that means is that you have a p orbital on the x-axis, p orbital on the y-axis, the p orbital on the z-axis. And when you look at the radial distribution functions for this, you'll see no probability near the nucleus, and probability dies off away from the nucleus, but you have this middle point of high probability. And when you plot that out, you get this tear shape. And they're not symmetrical shapes at all. It is this tear shape where you have a node at the nucleus. And that's how we know what the p orbital looks like. We're just solving Schrodinger's equation and plotting it versus distance. When you do that mathematically, you get this tear shape. The L equals 2 or d orbitals so you have n equals 2, L equals 2. Since L equals 2, you have 5 different types of orbitals you can have, and I'm showing the 5 here. One between the y and z axis, one between the x and y axis, one between the x and z axis, one on the x and y axis, and one on the x and z axis. You get some really funky shapes when you start looking at the d orbitals. So we're not going to look at the probability distributions for these, but you can see you have many nodes now in these d orbitals. But all you need to do for this class is be able to tell me the different m to l values, for the d orbitals, and be able to recognize what they look like. F orbitals, n equals 3, L equals 3 is your lowest level F orbitals, and they get really funky looking. So we're not even going to talk about them that much, just to say that a lot of them are 8-lobed. And so if you go into higher level chemistry, you'll start looking at the F orbitals. Again, all I need you to know for this class is how do I calculate these quantum numbers, and basically what do these orbitals look like. So not only shape do we have to talk about for orbitals, we have to talk about what's called phase, because remember, light's not just a particle, it's also a wave. And waves have what are called phases. They can have positive or negative phase. And this is very important when it comes to bonding, but let's just go over an example. So we have, here's the s orbital, and you see it's all above this line, so we can say it has a positive phase. Here's a p orbital. You have half of it above the line and half of it below the line. So we have a positive phase and a negative phase. And based on how these phases come together, you will have influences on bonding and energy of your elements. Again, we don't need to go into that. That's higher level organic chemistry. But for this class, you just need to know that phases can have signs. Lastly, we've looked at all these orbitals, and you might be wondering yourself, probably not, but you might be, why are atoms represented as spheres when we have these funky shapes where the electrons are found? It looks nothing like a sphere. And the reason that atoms are spheres is because when you add all these s, p, d's, and f orbitals, on average, where you're going to find an electron is in a sphere. So that is why we think of atoms as spheres. Alright, so that was very baby steps into the world of quantum mechanics. And that's the end of chapter 7. And so I will see you in the next video.